Hi everyone, welcome to MathSpellBook. I'm your host Peter, and basically we are going to engage in just studying math today. You know, like I don't have really like a big major plan on what we're gonna tackle first, so I think that's like the more fun part. It's like basically we pick out a subject of math that we feel like we should be curious about, and then just basically just move forward with that. So I think some of it's gonna be practice. So it's gonna be like some of the stuff that I haven't been touching for a while, even though I should be. Because like integrals, we definitely should practice. Integration techniques. Oh, you're already on that. Let's do integration by parts. Let's practice some integration by parts. I haven't, even though like I've done a couple of these before, sometimes I have to put myself back in practice because, you know, like sometimes when you don't do math for a while, sometimes it just doesn't come back. All right, here we go. Let's start with some basics here. And you know, sometimes like let's just make math more fun. So like, you know, let's just pick up something that we feel like we should practice and just go with it. So okay, so number 7. And this is just basically having us solve the problem, right? So let's just do this. So cosine of x dx. Pretty sure this is probably easy for a majority of you guys. So now we have to choose a u, and then we have to choose a dv in this case, because integration by parts, if you guys don't remember, and if you don't, that's okay. I think like the way the general form is written, I think you're given this form, and then you have to write it like this, where it's like du, something like that. Usually with the general forms, you just remember the general forms the more you do the problems. So like if you guys forgot about that, that's okay. So we have something to differentiate and something to integrate, right? So I think this one is going to be pretty simple because we can differentiate x, which will give us du as dx. So that's pretty simple. So now we have to have a dv. So I think this is the part that a lot of people sometimes forget because they think it's just u and v, but it's actually u and dv. So we'll put dv as cosine. So that means it's v is sine. Because we know if we differentiate sine, then we're going to get cosine. So now we got to put it in the general form now. So we're going to have x with sine of x, and then minus the integration of, so for So we have v, so this is going to be dx, which results in sine minus, well, technically if you integrate sine it would just be negative cosine, so put that there. And that's how we do the simple problem. So let's skip around. Let's just skip around. We're not gonna go like in order. So let's like just jump around and see where we can go. Oh, let's do one with a natural log. I think natural logs are usually a little bit more challenging. So, so 13. Let's just write 13 first, so that we know the number. And that one has x squared natural log of, oh, okay, so we need to pick a u. We also, I know there's also tabular, but I don't think this one is going to be good for tabular. Du here, just erase this because I don't know how much space we're going to need for this. Okay, let's see, which one can we differentiate that's not too cumbersome? Because we have a natural log here, and it's also given by x cubed here. So that part seems like it's going to be the most complicated. The thing of it is that we're probably going to have, in order to do this, we're going to have to do the natural log of some, we're going to have to do, hey Grandma Ursula, how's it going? Just basically doing some basic integration by parts. We're going to jump around a bit with the math. There's no real schedule on what exactly we're going to be focusing on. We're just basically going to be jumping around different math subjects. But how are you doing today? What's the best part of your day so far, my friend? So if we have this is tx, oops. So if we have this as x squared, then that means if we integrate it, it's going to be this. Doing well, lazy today. Just played some of. Oh, okay. Binding Isaac. Yeah, one of my best friend and his sisters like that game. I don't know if he plays it anymore, but I know his sister does. Okay, so if we're gonna have this as u, we're gonna have to do u substitution. That's gonna be a little bit. So it's u. And then du dx, and this one would be, well, it wouldn't be over x, it would be over u, so then it would be over x squared, well, x cubed, I should say. So then it'll be 3 over x. Maybe we'll also do some physics problems, because I haven't touched physics in a long time, and I probably should be touching some physics topics, actually. So I guess it's just a math physics day, freestyle. I don't know what I would put on the thumbnail for this. Maybe freestyle physics and math session. Because I think whenever I do just calculation-based math, I call it baby maths. There's going to be so many different terms in my YouTube channel. It's going to be like, okay, what are you doing today? And are you going to do it in a specific order? Nope. I'm just basically trying to have fun with math and hopefully physics too. Now where was I? Oh yeah, so... Oh yeah, there's have to be a dx afterwards, so I have to remember that. So Guys, if I forget, please remind me. So we're given, and then x over, do that. You know, this is a mess. I probably should just separate it with a line so that way you guys can see it. Now, okay, so now we have to do v by du, and that's dx. Okay, cool, I remembered. So now we can cross these out, giving us, oh, and this out too. Nice, everything cancels. That's what we want, guys. We want cancellation. Cancellation is where the magic happens. So, oops. I should put like equal signs here. That way you guys know where I am at. And it's gonna go back to its original form. And then we'll put plus C. Yeah, that wasn't too bad. You're on the right track with that substitution. Keep in mind you also do this problem with integration by parts. Yeah. Yeah, it looks like everything is... I think we did everything right there. Okay, maybe I'm not as far behind as I thought. I thought like when I do like problems, I probably will. Oh, let's do this one. I like number 16 because number 16, it looks simple, but it could be a simple one in disguise. It could be a hard one in disguise. So I'd rather just make sure that no matter what problem looks simple or what problem looks complicated, I want to see if I can do them. Okay, so for U and dv, we'll put U over here to make space for the dx. Okay, so if we have this, then if you differentiate it, it will be like this. Okay, and if we have x, then it will be x squared. Okay, and we end up with this minus I included U in the last one, right? Oh wait. I think I did something. I did an error here. Oh no, wait. It has to be V and du. Okay. Never mind. I thought I messed something up. Because the first form is usually U and dv. But then you have to basically change it to a... Okay, I nearly scared myself for a second, but that's okay. That's okay. At least we checked though. Because sometimes I don't develop the habit of checking my work sometimes, and I probably should do that more. Okay, so we have to do V. So we have to do V with du. Aha! And look, we can cross things out. Don't you just love it when things cancel? I know I do. And oops. Natural log. So that would be x squared 4 plus c. Cool. I like it when it all works out. Ooh. Here's one with a 3 stuff in it. Let's try 21. 21 looks really interesting. So I think 21 is x cosine sine, right? Ooh. This is very interesting because it has 3 things in it. I think we just found a challenge. When you're doing integration by parts and substituting by u and v, how you write that if you had integrate and differentiate the terms more than once? Yeah, I haven't run into those problems yet. That's actually a really interesting thing to keep in mind, actually. Okay, because in this one, I'm also double checking to make sure that I wrote the problem right, and that's the way the problem looks like, yeah. So now is, I don't think there's a trig identity that's like that. I mean, it's missing a 2, that's the thing. Because I think there's one where it's like 2 times cosine and sine, but I'm probably getting the wrong trig identity. Because trig identities I don't memorize. Unless they're like the very obvious ones that we're so accustomed to in calculus. For anyone that memorizes, or at least like can derive all the trig identities, and like they have a method where they don't forget it, I'm like, wow. They could probably solve a lot of math problems with that knowledge. So we have cosine and sine. I feel like this might be a trig identity of some kind. I just don't know which one it is. Because I feel like we can rewrite this somehow, so it's like 2 things instead of 3 things. Yeah, I keep feeling it might be that, although I feel like it's missing something to be like cosine times 2. I'm gonna Google it. Trig identity. Cosine times sine. Let's see what that is. Oh, it says it's half. It's like half sine. So according to this, it would be like x times sine of 2. Oh, hello, Palnun? Hopefully I pronounced that right. No, it's okay. It's okay. I don't remember trig identities either, so, you know, it's all good. According to Google, or at least Google's AI, it's like half cosine. Hopefully that's correct. Okay, so they say the double angle formula is like, it's like for sine times cosine. According to them, they basically said that sine to the 2 is equal to 2 sine cosine. So meaning that this would have to be divided by 2, right? I mean, yeah, that seems about right. Yeah, because like if you think about it, if it's like that property, that seems to make sense to me. Okay, so now we actually have it in 2 parts, which is what we wanted. Okay, now, so we have a 2. So what we can do, I think, to make it easier, we can put that outside, and we just have to remember. Oh, oops, I was about to rewrite it again. So what we can do is that when we do this process, we have to remember to put a half there. So, oh yeah, I switched up my Euler identities. It's fine. I forgot to read that part, that big paragraph you typed about Euler's rules and stuff. But that's fine. I would recommend one extra step in the substitution, but it's still correct this way. Okay, maybe when I'm done with the problem, you can tell me what your recommendation is, Poundin. Am I pronouncing your name correctly? If I'm not, please let me know how to pronounce it correctly. Where were we? Oh yeah, here. So, let's, so which one should we do? For du, we might get a double integral scenario. But we'll see, because if we integrate x, yeah, then we have to do du by dx, so I'm probably gonna do something silly, but it's like you like, I think like doing something silly is probably something that's worth doing, right? Especially with math, because you basically learn more if it's wrong. So 2x, so if we do sine of u, that turns into cosine, and then for that turns into 2, so 2 cosine u, so that would be 2 cosine x, and put a little dx there so we don't forget. Okie dokie. So sine of x2 over 2 minus so we're gonna need v, and then du, which is cosine 2 dx. Won't tell you, you have to suffer on your own first. I think like I understand what you're saying there, but I think the suffering thing we have to take out because you know, like everybody struggles with math. Like I'll let you struggle, not suffer, because a lot of people that go to school and they do math, I don't think like that helps them. Because when they say suffer, when you basically say you have to struggle, like suffer in the math, I think it's too much. It's too much pressure already. I try to take that out of my vocabulary when I try to like, you know, talk about math in general. I understand why people say it though, because it's just a struggle. It's not really suffering. You want to solve the problem, and you know, like you don't want the problem to be your own prison. You get what I'm saying? Yeah, it's too much negative connotation. Yeah, because a lot of people hate math already. The last thing I want them to do is like hate it even more. Because for me, I want to be able to make math feel like it's like you're going into your imagination and like you can basically just... I don't want to make it seem like it's like rainbows and unicorns, but still, I don't want to give the impression that people have to constantly feel like they're in a torture chamber whenever they're doing math. But people are like, but that's how I feel. And I get it, but at the same time, I'm like, yeah, but me making it worse for you by developing that type of language, I'm like, nah, I'm not helping you if I'm doing that. And sometimes when you get stuff wrong and you actually see an error with your problem, you're like, oh, wait a minute, I could have done this and do all this stuff. And then like you do a whole roundabout thing of like just trying to rework everything, and you realize what you should be doing. And sometimes those are the wonderful times of math, in my personal opinion. Even though I don't fully even though sometimes, at times, I don't appreciate it as much as I should. But that's my neglect to see, you know? There are certainly problems you have to suffer through, cause it's pages and pages of computation, but math is problem solving, and that is fun. Yeah, I think we have to replace suffering with struggle. Because the thing of it is that, like, when you think about it, when you're struggling with math, it's not like you're, I mean, hopefully you're not strapped to a chair and basically meant, like, calculate the trajectory of this nuclear missile or something like that. When you're struggling, when people struggle with math, it feels as if like they're kind of like they want to solve it so bad, but at the same time it's like they're neglecting the process. Like they're neglecting themselves of the process of actually just working through it, you know? And to them that's suffering, because it's like, oh, you know, it's like they don't want to be in that they don't want to be in that state of like, I know the answer, but I'm so close, but I can't get there because of this one specific thing. And that's usually where the most growth comes from. It's like when you're playing a game and you're like a Dark Souls game, and then like you're facing a boss, but the boss is so hard, and you just want to beat the boss so bad, but you're kind of like not thinking about the process of how you get there. And then you beat the boss and you realize that, oh, how did I beat them again? And you don't want to face them ever again. But with math you can't do that. Because when you stop doing math, you start forgetting what you do. But then, like, you realize, oh, there's a muscle in me that I haven't tapped into for, like, a couple of months or a couple of years. And then you suddenly just redevelop it. Now, wait. Now, cosine 2 is not the same, right? It's not the same identity as well, right? Or no, it is. Now I gotta think about my trig identities. I always end up Googling my trig identities because I get so forgetful on them. So it has 3 common forms. This is probably the most longest way I've done it, but there probably was a simpler way. Which one should we use? I mean, we worked with science. Well, that might make it harder. I totally agree. Pages of computation is essentially a high level. Yeah, I get that. Because these problems are just tedious and long. Yeah, I feel that. I already showed in grade school I can solve polynomial equations. Nice. Why do I spend like 40 minutes looking for zeros and polynomials in this polynomial? Yeah, that's true. And especially when you're thinking like, we have computers that can do this. Why do I have to learn this by hand? But, you know, like, you have to learn it because it's like you have to see if there's a flaw in the computer program, if it gives you like nonsensical answers, or if it's not doing a specific process that you know should be computationally accurate, or should be able to do something. Actually, Pauno, do you mind if I ask, like, are you a high school student? Are you a university student? Or are you a grad student? Or are you just someone that just loves math and physics? Actually, I'm trying to see if I should have done the V and U in the opposite way, but because if I made sine of then V would be that. I don't think there's any other way here. Should I just call you MathSpellBook, by the way? Like, you know, like, you can call me that. I also introduce myself with my first name, Peter, so you can call me either Peter or, you know, MathSpellBook, whichever you prefer. Whichever is easier for you. I'm just glad I don't have to calculate 2 long pages of operator forms and change basis and rewrite all my I do math for fun, and in the end up teaching it. Oh, nice. Then you probably could teach me a thing or two then. Like, do you teach at a university level? Do you teach like high school students? Like, which part of the educational system do you teach, or are you a tutor? Like, are you a math tutor? I should probably ask that too, because like we welcome everybody who loves math and is willing to put their energy into educating others. Let's see here. Yeah, I guess there's no other way around it. Yeah, sorry about that, guys. For some reason my internet is not restoring itself. And unfortunately, I don't have great internet, so it's gonna like lag a bit. But don't worry, if you're watching this on YouTube, like I'm recording like all of the footage on my end. Because it's still on red, and I'm like, it should come back to green, like, eventually, but this is the longest it's ever been on red before. Unless there's something seriously wrong. So the last thing I want to do is just unplug the modem. I might have no choice. We're probably gonna lose stream, but I'm also recording, so I'll just unplug the modem. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Alright, so basically I just resetted the modem, guys, so if you're watching this on YouTube, you're probably not experiencing it because this is all recorded, but like for the stream is probably going to experience like the stream going down for a bit, so to not keep you guys waiting, I will just but also I can't write anything because this is all a web browser too. So we're just gonna have to wait for a couple of seconds for like, apologies guys, like unfortunately, like my internet's not the best, so sometimes these issues do occur, so we're just gonna have to be patient for a bit. Yeah, because I almost forgot that the browser program I use to write also requires internet, so probably the next time I probably should use my other writing program. Alright, let's just give it a couple seconds. Yeah, it takes a while. It takes a while for it to reboot. Unless it's like one of those days where like the internet just like goes down for like another reason besides the typical ones. Alright, so okay, the internet, I think the modem is connected now. We just gotta wait for stream to be connected. Okay, there we go. Okay, we're in the yellow right now, so hopefully it goes back to green soon. And for anyone that's still watching the stream, we're back. We're back. Okay, now it's finally in green. I'm like, oh my goodness. Oh great, now it's going back to yellow. So we're not out of the woods yet, guys, so like let me know if the stream goes down. Yeah, my internet's not the best. That's the reason why like you guys were seeing a lot of fluctuations. But thank you for your patience. Thank you for your patience. Yeah, unfortunately, I don't have fiber optic, so I don't have like a really good internet connection. Okay. Oh yeah. So we're looking up the identity for cosine x. So according to Google, we can either have cosine, it could be either equal to cosine x minus sine squared, or 2 cosine squared minus 1, put these parentheses here, or have you looked at the connection of the trig functions and the complex? No, I probably should like look those up actually. It's really interesting and fun to unlock the derivation of many trig identities as well as the basic 80% of physics. Oh, okay. Maybe I'll take a look at that next. My very first attempt of stream was with 1 megabyte upload connection. Oh wow. Wait, so do you stream, Paunan? Okay, so ooh, these don't look nice. They don't look nice at all. Wait a minute. Maybe I'm doing something wrong here. No, it's supposed to be DUT. Okay. I do not. I tried a few times, but it's not for me. No, that's fine. That's fine. I think like whenever I stream on my gaming channel, it does take a lot out of you. Like when I play video games. But when I stream here, I feel like I'm more energized to like learn because of you guys. Because like I know some of you guys are like more knowledgeable on the math side. Even though I know I don't do things like entirely right, because like sometimes you guys know more than me and you're telling me to do something, and I realize that wait, what am I not seeing that they're telling me I should do? It feels like I'm a surgeon, but I don't know that much about surgery yet, and then suddenly some doctor in the what do you call it, in the observation deck, they're basically like, no, use the scalpel. It's like, no, use the sponge. And I'm like, which one's the sponge? Which one's the scalpel? It's like stuff like that. Not to mention, I usually play boring stuff. It's not worth streaming. I mean, what type of games do you like to stream? Or like, what type of games do you like to play? I usually play like gacha games. Or video games that I just like in general. I don't know what that is. It's more like trying to edit something in Photoshop and someone who spends many hours. Oh, okay. It's going back to what I was saying in that scenario. Okay. Actually, Paolo, do you mind if I ask where you're from? Because I know with like where I'm talking, like, you know, like there could be like a lag in between, like, you know, what I'm saying at this current moment to what you're observing on your side of the stream. So I mostly play like city builders and they tend to be slow. Oh, Italy. Okay. I mean, city builders can be fun to watch because, like, you know, like you're building stuff. The thing of it is that like I think with city build, like if you're building things, like if you're doing like those games where you just build towns or like, you know, Sims or something like that, I think it could be like entertaining to watch because like you're building stuff, but it's not too brain draining where it's like you have to focus on a boss. You're just basically building stuff to make it look nice. And like you can basically have a conversation with chat at that point. I think I have to get into more building games actually. I just haven't found it. Like the only building game that I ever played on my game stream, my video game stream channel is Townstar. But do I want to do this scenario though? I feel like it's not gonna really go well. I mean, if we do, I feel like we're gonna have to do the old calculus. trig identity that we've become accustomed to, but I don't like it. I really don't like it. It's just very convoluted, but I guess we might not have any choice in the matter. Now, I have to remember, because I do believe this one is it plus cosine 2? I'm probably making more work than I should, which is more likely, because that usually happens. We need these anymore. And plus you guys have seen me make mistakes on the channel a lot of times, so, you know. If I make a mistake, I make a mistake. Maybe simplifying, maybe making it smaller will make it a little less intimidating. I'm pretty sure that all of you guys that worked out like math problems in the past are like, wait a minute. Oh, no. Never mind. If this was a plus, then it would have been much better, but it's not. Because then we got an, oh no, the 1 disappears. Dang. Oh well. Oh well. Can't. 2. Wow, we go back to where we started. That's funny. That's really funny. That's really funny. It reduces into itself. That's really hilarious. Unless I did the math wrong. Let me see. Let me double check. But I think that's hilarious. That's very funny. That's very funny. That is useful though. In Austria, we say that there's always a multiple paths to Rome. Yep. Try labeling your integrals as a letter, like I. Multiple paths lead to Rome, and this guy is stuck in a roundabout. That's true, that's true. But I think this is where you actually have to, like, enjoy the struggle, because it's like... I think that's really funny. It's like, basically, you struggle with a problem, but then you're like, ooh, where does this go? And then you realize you end up where you started, and I'm like, oh, interesting. That's very interesting. It is unironically useful. You get that your integral is equal to one evaluated term minus the original integral. That means 2x your integral on the left hand side. You might be onto something. Okay. Let's well, first can I copy this? I don't want to rewrite it, but I just want to copy this one. Oh, this is the problem because I'm left-handed. So we'll copy this and then paste it here. Yes, allow please. Okay. Because this is what we started with. So let's erase that. And on the right hand side, we had a half times minus oops, I didn't need to write that part actually. Yeah, like that. Okay. Okay, there we go. Oh, you guys typed up some stuff. Let me see. Did you not end up where you did, and you did not end up where you started? He did. He simplified the. Oh wait, there's a sign at the start, not the cosine. How are you writing out? Out of curiosity, with the mouse. No, I'm actually using a stylus, or I guess you can call it like a. I guess that's what they call it. You know, the pen for a tablet. Let's see. I should pay more attention to the problem when trying to. No, it's fine. It's okay, because you guys can only see what I see, and sometimes I don't observe everything. So that's something to keep in mind. Okay, so I mean, we can just multiply 2 on both sides, so we can get rid of that half. There's no rule that says we can't. Because, I mean, that was the clever way we removed it, right? So. So that way it's, like, much easier for us to, like, look at. Okay. Alright, so now no, you know what? Maybe doing that was not a great idea, because we're gonna have to put it back in anyway. So yeah, so I thought I was being clever by doing that, but then I realized no, we gotta put it back in. And that won't be helpful. So do that. Just half there. Okay. We had a half out here. So okay. So I'm guessing we're gonna have to do U substitution again. Well, not U substitution. What I'm talking about, integrating by parts again. That's what I mean. So sine of 2, 4. Then half here. And then Okay. So U, V, du, and dv It's unfortunate that the term next to the x squared is not 1 plus cosine 2 or 1 minus cosine 2, because then we can basically like change it up easier, but I don't think that's gonna help. That's not gonna help. Yeah, integrating with cosine is not gonna be, because I feel like we're gonna, oh, maybe we're gonna end up with the same thing, like, but we have to do it twice. That might be the thing that we're gonna have to deal with, I think. And then dx, that's too close. I'll make some more space so you guys can see it easier. Dx dv is, oh no, not cosine, oops. X squared, and then for v we have x cubed sine 4 minus, and then we do all this all over again, so 3 sine of 2, then minus sure, if you would like to. Even though, like, I'm struggling, I do like writing stuff. I do like writing, like, the problem, like, because it makes me feel like I'm like, it makes me feel like I'm a theoretical physicist writing stuff on the board, even though it might not make total sense. Whenever you solve something by integration by parts, you most likely want to differentiate the polynomial, since it will eventually disappear. I mean, that could be, yeah, that could be the reason why I'm like in this loop here. Yeah, we'll do that. We'll do that. That's probably what I should have done in the first place. I think the reason why I didn't I integrated, because it was just like easier for me to do it in my head. I don't really like integrating like the trig functions, but I guess we have no choice in the matter. Okay, we'll go by your suggestion, Palin. Okay, so when we integrate this, so we have cosine here, and du dx. So that means we're going to end up with half cosine u of du, which is sine of dx. Yeah, sine of dx. I probably should have done that in the beginning. And then dx. out. Yep, there we go. That's like so. I think we can just put the half in. So like that. Okay, and on this side, I think I'll move this up because you can't see in the bottom here. So I think before we had half times 2x. Sorry, there we go. Yeah, I kind of figured that it was going to go into this route. Because usually when it takes longer for integration by parts, this is usually the result. Just put the line there so you guys can see it. So, that way. And then we have to minus that, so... But thank you for the suggestion of pound. Did this calculation right. So. Okay, because then these two would cancel out. That is if I did everything right. I want to make sure I'm not missing anything, because I feel like I'm missing something. Yeah, so that goes into there. That's why it's that like that. So this part we don't really... So we can ignore this part. Yeah, because then we multiply it, and oh yeah, we had to write this part. Okay, so that goes into that. Okay. Oh yeah, we rewrote it right here. Okay, so right here. Okay, it looks like I did everything correctly. So then, yeah, this would equal 0. So then plus a half, just then again, there would be a little constant there, but we're not going to do that until the end, actually. this looks right. Yeah, then we have a half here. That would equal 1. Yeah, sure. If you want to give this, if you want to give a second tip. Oh, we're in the. Oh, cool. We just went back to green because we were at yellow before. Did everything right here, so this would equate to 0 in this case. Oh, well, then again, then that means that the negative version of this one equals that one. Unless I'm yeah, probably I should have done that in the beginning of the problem, what you suggested. So 21, we have this, and then we had that, so... So... you could probably do the whole problem all over. So... it was x cosine x sine of x, and then we changed that to basically x cosine 2.5, and just reduce that so it's like sine of 2, and now turn that into du dx, then oops, that's supposed to be dv, so dv sine of, and then we integrate it. I'm just gonna make sure that I remember the principles, so I think it's gonna be half, and then cosine, oops, no, it's supposed to be sine of u to u, which gives us negative cosine, so negative cosine 2. Okay, and then if we rewrote this, we would basically have negative x cosine over 2 minus negative a half cosine 2 x dx. Yeah, there we go. And I think we can move that into the front, so y times a half, and then we have cosine like so. Move this up, then this would be cosine of u du, leaving us with cosine actually that'd be sine 2x 4 plus c check it over. Okay. Yeah, it's negative cosine here. Did the u substitution, that gives 2, and then yeah. Okay, that looks like it's right. Let's take a look. What did I miss? We have to put, oh yeah, we have to put v in here, and we did that, and then du, which is dx. Because what we originally started with was this x sine of x let's see. Yeah, that's right. Over here, if it's sine or negative cosine, just half. Yeah, if you integrate that, yeah, that's what you end up with. Then over here, minus cosine. You started with the half integral. Yeah. Oh yeah. That's right. Oops. Thank you for seeing my error right there. Thank you, Grandma Ursula. I mean, it feels like everything's correct. I've checked it over twice. Unless I'm missing something, but I feel like I didn't miss any steps. Just call me Benedict. Dang, why I gave myself this tune. It's fine. It's fine. It's alright. Maybe I should just call you Ursula since it's in the name, and that way chat doesn't get confused when I talk about you on the chat. When you integrate something, you have to apply the chain rule. I thought I already applied it. Are you talking about this part? Because I already applied the chain rule to it. Like this is a U. Unless you're telling me that I missed somewhere in the middle. Let me check. Maybe I didn't differentiate right. Or integrate right. Let's see. Because you integrate this, took it to U, and then basically that would be a half as U. I mean the left term. Oh, you're talking about just integrating it? But, you're talking about this term, right? You're talking about this term, right, Ursula? No way, I'll write it up, send it to you on Discord. Yeah, you can post it on Stream Material Resources. You can post it on that channel. Let's see. Let's see here. I'm actually checking what I missed here. Because it seems like, let's see. Because when we integrate this, then yeah, we turn this into U, and then that give us X. Cosine. Yeah, I feel like I didn't do. I feel like I didn't miss anything. What number is this actually? It's number 21, right? I feel like I didn't do anything wrong here. This is chapter 7. So let's see, chapter 7, 21. If I get it wrong, I get it wrong, and I can check over what was my mistake. So, oh, I forgot to check what's, oh, I think it's integration by parts, right? So it's 7.2. chapter 7. Okay. That is interesting. So it looks like they... Well... I mean... I mean... Wait, what did they write? It's just that they multiplied a half with this side. I mean, that makes sense because we're just trying to solve this part. So technically we are technically correct. It's just that you have to multiply a half on this whole thing here. Yeah, because then when I think about it, we were just doing this part here. Yeah, that makes sense. So I guess we just missed that one little part there. I thought it was completely off, but I guess not. I guess we were just off by just a factor. 8? Oh no, wait, this is 8. This is 8, and this one is 4 plus C. And this is all equal to okay. That was a pretty interesting problem, actually. I had to like actually look at the back here to see, but that was actually a pretty interesting problem. Took some, we did take some twists and turns along the way because we picked the wrong things, but I think that's part of the learning, like basically just learning it. I think that's pretty cool. But you know, sometimes when you do multiple problems, you can encounter the ones that you have a little bit of struggle time with, but that's usually how it be. Let's read about tensors a little bit. So if you guys want to post anything like that helps me with a problem, you can post it in the stream material resources channel. Okay. Actually, I just want to cover some tensors because I haven't covered tensors in a while. I also should open another book that I have on, let's see, Student's Guide to Vectors and Tensors. Open with my browser. Because I know there's a section on, yeah, here we go. Covariant and quadривariate components. I just want to briefly go over stuff here. So it looks like they tell you about the gradient So they kind of briefly go over some stuff that you have to know. Yeah, here are the components things, like the subscripts and the superscripts. I had to look at my tablet and restart my Discord. That's okay. That's okay. Yeah, we were just missing one step because I realized that I had to really think about it a bit. Like, but I see what you. So if you guys are curious, this is what Ursula posted. Yeah, it's much more simple and sweet. So thank you for posting that, and also thank you, Paul, for posting yours as well. So I'll actually will show yours as well. So thank you guys for actually being awesome help, because both of you actually help re-educating me on integration by parts. I think this is fantastic. You guys are posting your own solutions there. So it allows me to relearn everything that I forgot about integration by parts. I usually write on a tablet and send the image on Telegram and copy and paste it. And yeah, I mean, do whatever is easier for you. Oh yeah, here we go. They start talking about the metric here. Yeah, I think we should cover like a little bit about tensors and vectors for about a half an hour, because we got like half an hour of stream left because we spent a majority of it on integration by parts. But you know, it's good to get some practice in from something you know and then learning something new. But let's see. Okay, covariant and quadravariant components. I've struggled with these for a long time because like I have a kind of an inkling of what they're doing, what it explains, but at the same time I'm like, it's like hard for me to actually implement it. After you got your exercise in integration by parts, you are fluent in it. There's a quick method to quickly and without much brain power to do it. Yeah, I know there's like tabular. What's the DI method? I don't think I've ever heard of that one. I know like there's like tabular and actually with that problem, when I think about it, we could have done tabular. I just realized that now. Yeah, I just realized we could have done tabular now because we only had one x. We could have differentiated x and then integrated multiple times. Yeah, that would have been easier. That would have been easier, actually. Oops. Because I think it's because I didn't learn tabular in like when I took an actual calculus course, that I don't think of it right away until like I actually have to like look at the. I didn't look at the problem clearly. I probably should have looked at it more, because then I realized, oh wait, we could have done tabular with that. Well, oh well. That's gonna be in the video anyway. They're the same? Okay. If we had a Frenchman in here, he probably would know it by another name. Oh, okay, okay. That makes sense. Just give me a minute, guys. I will be right back. We're back, guys. Sorry to keep you guys waiting. Lots of theorems and stuff usually have their own name depending on the country you study in math. And yeah, because I think when I was reading a Japanese math book, I'm trying to also learn Japanese like through stuff I like to learn. Like, you know, like I bought a math book that's mainly focused on math news and physics, and it's in Japanese, so hopefully I'll be able to learn some terms from like in Japanese concerning math. And it's funny because I think they also I think for certain things about trigonometry they phrase things differently, which goes in agreement with what you said, Paul. Okay, covariant and quadravariant components. Okay, because I'm familiar with some of the technicals of them. It's just that I think for me it's like you know when you learn math and it becomes like a second muscle to you. Like for me, I haven't developed the muscle for quadravariant and covariant components. It's like when you know how to do a cross product and it's like deep in your head that you basically just can do it on the fly, like the basic ones. Like for me, it's like I'm trying to think about how to think about these components in a way that's like kind of like working out my muscles to like make it easier to retrieve in my mind. Because where is it? Because when they show me images, I understand I kind of see what they're getting at, but at the same time, it's like hard to visualize in some ways, if that makes any sense. Have you tried transforming component systems yet? I would do that first before you tackle this. Are you talking about linear transformations? Because I probably need work on linear transformations then, if that's the case. Because according to this book, they say they mostly cover mainly vectors. I think this is all the physical applications of vectors, vector operations. Like I'm familiar with dot product and cross product. And it's really interesting that they actually make you learn the different component systems, like spherical and cylindrical. I mean, we could practice these, because I haven't done gradient or divergence and curl in a long time. I probably should practice these too, actually. Because I remember when I was learning these, I was like, oh, it's like a more involved version of the dot product and the cross product. Because this one is a vector, because you basically are just like differentiating it. Like partially differentiating it. And the divergence, this one's like the dot product. And I know with curl, it's sort of like the cross product. So I know when you actually do the differentiation with these things, I know they also are involved with, like, you know, developing your intuition for tensors. Because I know when you convert into spherical coordinates, it gets a little wonky. And I think like the metric tensor with the spherical coordinates looks really, really convoluted. So I know this is the divergence. So this is the divergence. So hopefully you guys don't mind me saying my thoughts out loud. Because usually when I write notes, I don't really focus on the thing I'm writing. I usually focus on the note, like actually writing the notes, which is probably like bad because it's like I know I'm taking these notes to remember the stuff I learn, but I merely focus on just writing the actual thing that I'm writing. I don't even like think in my mind that of the topic that I'm actually writing on. I don't know if that's ever happened to you guys. I might as well probably have like, what do you call it, those like voice recorders next to me. It's like day 772 learning tensors. The tensor seems to be involved with the subject known as the vector. Okay. I have to remember, does a negative divergence mean that something is spreading out, while a positive divergence is something going in? I have to remember what that means. Because I always get them mixed up. Because I think a negative divergence is when something is coming out of the point in question, while the positive divergence is when things are being sucked in like a drainage, like a drain in a bathtub. But if I'm getting it wrong, like let me know in the chat. It's the other way around? Okay, yeah, I got a feeling, because I always mix those things up. So when it's negative, basically it's X. Think of negative as sink and positive as radiating. Yeah, I was thinking that, and something told me in my brain that I was mixing it up. That's why I mix them up a lot, because I'm like, oh, is negative supposed to be sink and positive supposed to be radiating? Because that's what kind of that, like, when I think about it, I was like, oh, maybe I should have my in like the story I want to write, I want to have like the main characters, like I can actually visualize this as like the characters like making a projective field, or making like a, like, you know, maybe a vortex of some kind to fight off like the foes that they want to fight. They have to know things about gradients and curl. But for curl, I think it's a little bit more complicated for me, because like I mean visually, because they go into so many different dynamics here. Let me see, what is the simile they used? They used a paddle wheel, right? Yeah, they use a paddle wheel. The direction of the curl along the axis of a paddle wheel. By convention, a positive curl direction is determined by the right-hand rule. If you curl your fingers to the right of your right hand along the calculation direction, your thumb points in the direction of the positive curl. Where's the picture they showed? There was like a picture here. Oh, okay, here we go. I'll zoom in a little bit. Actually, I forgot what positive curl and negative curl means. Because I know with curl it's a vector. It's a vector because it's sort of like a more function version. Well, this is how it is in my head. It's probably not the way to phrase it. If since I'm not in higher maths yet, I usually think of it as sort of like a function, a vector function version of the cross product. So we have one current up here, and two. So I'm guessing the paddle wheel is like up here and like in between two, like 1 and 3, and then 1 and 3 are acting as like currents over here. It's a vector field like a function, but instead of having a scalar value at each point, there's a vector at each point in space, right? I mean, this is practically like the last parts of multivariable calculus, right? Like basically divergence, curl, and the Laplace and the gradient. Because I know the gradient is just basically the derivative of is it a vector field? Or does it just turn a vector into a vector field? Or a function into a vector? I'm probably saying a lot of things wrong, but usually like when I have an idea, it just basically just like manifests itself based on what I know. Like, I'm probably not phrasing the right terms. Because I know this is going to come in handy like when we get into like, I think like making basis matrices. Because I know these extra terms are going to be like in the matrix if you set it up as an identity matrix. Oh, it's raining. For some reason I like the rain. Maybe that's the reason why the internet was like going in and out a little bit. Like probably like the storm was already brewing. Because sometimes that happens. If you think of 2D function like a mountain, the gradient indicates the steepest direction of descent. Yeah, because like a positive gradient means like you're at the highest point, right? While a negative one is like you're at the lowest point, right? Like you're at the lowest point of descent, right? So it points to where the function increases most rapidly, right? Because I know with the Laplace, it's sort of treated as like the second derivative of the function itself, or at least of the vector field. Let's see what we got the problems here. Scalar product. Let's do one involving the stuff that we were talking about, curl and divergence. Curl and divergence and gradient. Triple vector product. No, I think that's too tedious. I don't want to do that one. For the function, find that one. I think that one's easy. I don't think we should do that one. What is the? Oh, I actually like this one. Well, this... No, actually, I think what I'll do is do this. Oh, it took the highlight. I didn't want that. So... like so. Copy. And paste. There we go. Okay, so we are given this function. What is the gradient of this position? I just want to get more practice with it. So if we think of the gradient, it has to be of x. So then here, and then of y, meaning vector field. Now I think we have to put like I and j here, and at position 3 and 2. So just yeah, I think the I and j there is necessary, because then we have 3, which would lead us to 6i plus oh, this should be negative. So negative 4 4j. Sometimes you just get so excited to solve the problem you just forget that you are on the eraser button instead of the pen button. I think that's correct, because if we think about it like this, okay, yeah, 3 times 2, that was, and then negative 2 times 2. Yeah, that looks good. Let me see here, because I remember there was the website for the answers, so. Here we go. Yeah, this is chapter 2. So this one is problem 2.7. So 2.7. Yep, that is the problem we're dealing with, so. Yep, there we go. That's the answer. Cool. What's next? Find the divergence field of the vector. Oh, okay. Another interesting one. So we're getting into divergence. So time for my memory to actually start trying to remember stuff. There's so copy. Sometimes, like, when I try to learn, like, higher levels of math, like, I worry about, like, skimping out on the things that are most important. But at the same time, like, I don't like it when they drag on stuff and then it's like, oh, I'm learning this, but then you realize that it's not on, like, the next topic of math that you need. So it's like, which parts do I have to focus on and which parts do I don't have to focus on? It's like stuff like that. Find the divergence vector of the field given. So if we remember the divergence is this, and I think we'll just do it like that. So it's a dot product of this one, we have 5y. It should be 5y. 5y plus. Well, actually, this one goes to 0 because there's no y in it. This one goes to plus 10z. And I think that is the answer. If we double check here. Oh no, wait. This should be a plus. But then again, this goes away anyway. But luckily I caught that though. This is plus. Okay, 5y plus 10z. Alright, so continue with problem solution. Yep, there we go. Excellent. Oh, now they want the curl. They want the curl for this one, so we don't have to copy and paste that. We'll do it. Okay. Curl. So that means boom, boom. Oops. Boom. So we're going to be left with C. X. C. Yeah, maybe tomorrow I'll actually do some physics. And hopefully we can implement the math that we learned here into like some physics problems tomorrow. So we got xy negative x. Okay, the fun part. Putting them all together. Okay, so first off is C, then I think that's X. Yeah, that's X. That's I, and plus I think everything is going to practically go to 0 at this point because it doesn't look like all the terms are like going with their respective integrations. Well, not that's the wrong way to phrase it. I guess I've just been focused on one problem before that. I'm like losing my ability to communicate. Oh, here's one that matches. Minus. Oh, why'd I write a 2 there? So K is the only one that's going to be left. Because, like, if you differentiate that, that's going to be 0. Differentiate this, that's going to be 0. Differentiate this, that's also 0. This is also 0. So we're going to be left with a curl that's going to be -3 minus 5x. And that's all going to be multiplied by k hat. I think I'll make this look a little bit more compact. Oops. Yeah, there we go. We got the same answer. Perfect. What's next? Find the Laplacian. Oh, okay. Cool. We're actually doing the things that we want to do, like basically just doing them step by step. Maybe like tomorrow we'll probably continue on with these problems. So this one, the Laplacian. So I think first we're gonna have to do the gradient first, and then we're gonna do another differentiation. That's like the easiest way to go about it, I think. But then again, we already have the gradient, so might as well just do the gradient. It said 2.6. Oh, this one. Okay. Yeah, okay. So we might as well write that one down. So first, the problem we're dealing with. This function. Copy, paste that, stretch it a little bit, and they want the Laplace of this function, so we'll do the gradient of this one first. Okay, so I don't think we need the for z because it doesn't look like it has z's in it. So in this case, we have 2x plus 2y plus 3, and then plus for the y's we have, and then plus 2x. So then these two together, oops, 8 plus, okay, that's the first part. Now we have to do it again. So that means we are left with 4, then plus 8. That would leave us with 12. Oops, I didn't mean to activate this. Close that. That looks about right. So let's see. Oh, what did I miss here? see what was wrong with my thought process here. 2y here, yes. And then 3x. There's no negative sign, so I didn't. Yeah, that is 6. That would equal 8. Oh, okay. I think I see what I did wrong. So that just leaves 2 and... Okay, okay. So you still have to keep them separate. Okay, so I think I see what I did wrong here. So you still have to keep these separate so that you can apply this to this and this to this. Okay, that makes sense. So the way it should be written is though that even though you got that part, you still have to take this with this and with this, thus giving you, okay, plus giving you 8. Okay. Alright. So I gotta work on not to get tricked by the plus right there. Okay. So I guess the last problems that we do at the end of like the ones that we can handle, or like the ones that actually get me to think about like the deeper idea between them. So it's interesting. Okay, so we learned a bit. So we learned more about integration by parts. Just as Pound suggests, go with differentiating the polynomials, because the polynomials will disappear much quickly. In addition, when it comes to doing the Laplace, always remember that the part you're integrating has to be with the second part that you integrate with. I mean, differentiate with, sorry. The thing that the variable you're differentiating to has to be also differentiated by the next part. So, yeah. I sent you something to quickly wrote up about co and quadravariants. Hope it helps a bit. Sure, I will take a look at it. And if you guys want to see, I will present it to you guys. Thank you, Ursula, for posting this. So if you want to check where this is, it's in the Stream Materials Resources channel. So you can actually check out what Ursula, aka Grandma Ursula, posted there. So I'm definitely going to check it out after stream, but thank you guys for joining me today. I will be posting this on YouTube if you're watching this on Twitch. So yeah, so anyway, I think that will do it all for today, but thank you for joining me today, guys. Hopefully you guys enjoyed basically just doing math with me, and hopefully by tomorrow we'll do more on vectors and get in a little bit of tensors, and maybe we'll get into physics as well in there, because I think there's a chapter in this book that does vector applications, and that's where mostly the physics lies. So we'll definitely get into that. But thank you guys, and always remember, everyone is precious. You guys are just as precious as everyone else, and I will see you guys on tomorrow's stream. So take care, guys. Bye-bye.